Okay, hello everyone. Welcome to this week's C3 AI DTI seminar series. C3 AI DTI's mission is to attract the world's leading scientists in a coordinated and innovative effort to advance the digital transformation of business, government, and society. And this weekly seminar, we feature research that are interdisciplinary and is at the intersection of machine learning, computer science, engineering, and operations research that to solve the breakthrough of the research topics that brings or enhance the welfare of the society. I want to pause for a second here to thank our supporters as well as collaborators from both the academic and as well as the industry partners. We have a very exciting series this semester with the focus of the theme being the incentive design and learning for societal systems. We have 4 more talks for this semester. You can find their talk information, including the title, speaker bio, and abstract on our website. We have also had a pleasure to have had a very fantastic talks in the past few months. And if you have missed those events, please follow our newsletter and also find their talks on the YouTube channel. Okay, so it is our great pleasure to have Professor Milind Tambe to speak and share his work on AI for social impact, results from deployments for public health and conservation. Professor Tambe is the Gordon McKay Professor of Computer Science and Director of the Center for Research in Computation and Society at Harvard University. He also directs AI for Social Good at Google Research India. He is recipient of many prestigious awards that includes IJCAI John McCarthy Award, AAMAS ACM Autonomous Agents Research Award, AAI Robert Engelmore Memorial Lecture Award. He is also a fellow of AAI and ACM. He is the recipient of an Informs Wagner Prize, a RISK Prize from Military Operations Research Society, and the Columbus Fellowship Foundation Homeland Security Award, along with the commencement from the U.S. Coastal Guard, Federal Air Marshal Service, and Los Angeles Airport Police. So the talk will be about 15 minutes, and we will try to answer most of your questions for the Q&A session. So please feel free to comment in the chat as well as leave your questions through the Q&A. Thank you very much. And so I will give the floor to Professor Tambe. Thank you. Professor Tambe, you can share your screen now. Yeah.
Thank you. Thank you very much for inviting me to this wonderful seminar series. Thank you for all the organization. So I'm going to talk to you today about AI for social impact. For the past 15 years, my team and I have been focused on how to advance AI and multi-agent systems research for social impact, focusing on topics of public health, conservation, and public safety and security, with the key challenge of how to optimize our limited intervention resources. Let me just jump right into the lessons that we've learned. First, achieving social impact and AI innovation goes hand in hand. Concrete example is work we've done in public health. Here we have large populations to serve but limited number of public health resources. In the work we did in Los Angeles, we worked with youth experiencing homelessness. The goal was to spread information about HIV amongst these youth experiencing homelessness. We are able to show that our social network influence maximization algorithms are far more effective in spreading HIV information and reducing HIV risk behavior compared to traditional approaches. However, this work required innovation in the area of social network algorithms. With respect to conservation, we have large conservation areas to protect limited number of ranger resources. Concrete example is work we've done in Uganda and Cambodia. We're harnessing past poaching data. We are able to predict where poachers set traps or snares. And for the past several years, have been able to remove thousands, if not tens of thousands of these traps. However, this work requires innovation in the area of what we call green security games, which combines machine learning and game theory. In the past, in the area of public safety and security, we've contributed a new model called Stackelberg security games. And based on this game theoretic model, developed new algorithms that have been in use by security agencies in the United States, such as the US Coast Guard, the Federal Air Marshals, and others. You may think that these are very different areas of application, but they are all tied together by the underlying models and algorithms drawn from the same area of multi-agent systems research. A second lesson is all of this AI for social impact work requires partnerships with communities, with nonprofits, and with governments. Shown here are logos of some of these organizations. And our ultimate goal is to empower these communities to use AI tools and avoid being gatekeepers to AI technology for social impact. Third lesson is that in AI for social impact, the entire data to deployment pipeline is important. This is not just about making methodological contributions. We begin our work by immersing ourselves in the domain, trying to understand the data available to a nonprofit, the kind of problems they face. A predictive model then makes predictions on which of the cases faced by this organization are high risk versus low risk. Unfortunately, we don't have resources to deal with all of the high risk cases. Therefore, prescriptive multi-agent reasoning algorithm recommends to us which cases to actually intervene on. And finally, field testing and deployment is crucial, not only because we want to test our models in the field, but because social impact itself is a key objective, is a first-class citizen of this AI for social impact universe. If there is no actual social impact, then it is not AI for social impact. Today, after this introduction, now let me introduce the 4 projects I've selected for you to present to you today. In each project, there's a method and an application. 3 from public health, 1 from conservation. The first project is from Google India. The others are ones we've done at Harvard. And I'll cover papers from the last 5 years in describing this work, focusing on real world results, although there's lots more simulation results in our papers. And I'll recognize the PhD student and postdoc who led the work by putting up their picture in the top right-hand corner of the slide on which their work is shown. So let's begin with the first challenge of maternal and child care. So the United Nations Sustainable Development Target says that by 2030, maternal mortality ratio, mothers dying during pregnancy and childbirth, should be below 70 for 100,000 live births. Where are we today? Western Europe is very low. United States is more than double that. And actually the rates of maternal mortality rates have been growing in the United States. Unfortunately, countries like India are above 100 in terms of compared to the UN target of 70. And that's where we begin today. So in India, the situation is difficult. A woman dies in childbirth every 15 minutes. 4 out of 10 children are too thin or short. 2 children under age 5 die every minute. We are very fortunate to be working with a nonprofit called ARMMAN, which works with 26 million mothers, beneficiaries, and is present in 19 states in India. We are inspired by the words of the founder of ARMMAN, Dr. Aparna Hegde, who says that pregnancy is not a disease, childhood is not an ailment, dying due to a natural life event is not acceptable. So we are very inspired, but what can we do with AI? And that's one of the big challenges, to figure out what is the right problem to work on in collaboration with agencies such as ARMMAN. In this case, we selected a problem which is based on one of their programs called Mitra, or Mobile Friend. It's a weekly 2-minute automated voice message to mothers, to new or expecting mothers. So there's 141 messages that go out, voice messages. A message may be of the form, you are 3 months into your pregnancy, you should use this health supplement. Or your baby is 3 months old, enroll the baby in a government program. ARMMAN has shown that mothers who listen to these voice messages get significant benefits for themselves and their babies in terms of health. In fact, 2 million women have enrolled in a Mitra program so far. So where the problems come in? Unfortunately, 30 to 40% of mothers who enroll over time may become low listeners or drop out of this Mitra program, thus not getting the benefits of this program. ARMMAN generously helped us tour their sites, the hospitals where they enroll mothers, locations where they work in. We visited the home of one of the beneficiaries to describe it, I mean, I've grown up in Mumbai. I know what these homes look like, but just going inside and understanding what circumstances these mothers are in was useful to understand. This is a family of 4 or 5 that lives in $100 a month with $50 per month going for rent in a single room home that is half the size of my Harvard office. So you can understand why these mothers, they find it difficult to keep listening and become dropouts out of the program. Our task then is to help ARMMAN with their limited intervention resources. They have a service call center from where they can give service calls to these mothers, but they can only do so to a small number of beneficiaries, to listen to the concerns that the mothers have, to address them, and try to get them to continue listening to the messages. So example could be there's 100,000 beneficiaries enrolled at a time. We have to choose 2,000 of them for service call per week. Which 2,000 should we select so as to maximize the total number of health messages that they listen to? Let me give you a simple example to think through this. Imagine you have a call center health worker. She has 5 mothers under her care. 4 have listened to ARMMAN's voice message, a Mitra program message. 1 shown in green has listened to this message. 4 shown in red has not listened to these messages. So this health worker now has to choose 2 mothers to call. She could choose the first 2, which are shown in red. As a result of her call, this was a good choice. The 2 mothers turned to green. They started listening. The third one, who was in red, also turned to green on her own. Now the worker has to decide who to call next week. She may choose, in this case, these 2 who are shown in red. But this turns out to be a bad choice because not only those 2 remained red, but the ones who were green before have also become red. So the challenge here is that a call may not change a beneficiary state. A beneficiary state, on the other hand, may change on its own. And yet we have to prioritize 2,000 beneficiaries per week. We cast this problem as a restless bandit, where we are choosing K out of N arms per week, 2,000 out of the 100,000. For a restless bandit, for those who may not be familiar, each arm is a Markov decision problem. Each arm models 1 mother or 1 beneficiary. So a mother might be in a bad state. She has not listened to a voice message, or a good state. She has listened to a voice message this week. An action that we have could be to not intervene, not give her a call, or intervene, give her a service call. When we don't intervene, the probability of transitioning from a bad state to a good state may be low, 0.2. When we give her a service call, the probability may grow from a bad state to good state may grow to 0.8, for example. In reality, of course, we have 100,000 mothers, so we have all these different MDPs. We have to choose 2,000 of these arms. This is a very difficult problem. It's shown to be p-space hard. And so here, one approach is to compute a Whittle index based on the current state of the arm. A Whittle index essentially is computing the benefit of intervention. Technically, it's a subsidy that's provided so that the expected utility given a passive action becomes equal to expected utility given active action, meaning intervention. But for the current discussion, it suffices to understand that the Whittle index is computing this benefit of intervention. And we use an algorithm we developed in 2016 to compute this Whittle index and then rank all the mothers and choose the top K. Now, one key challenge here is normally when we compute Whittle indices, we assume that the transition probabilities, the model parameters are known. Here, these transition probabilities, that is how the mothers will behave, is unknown. So what can we do? We have limited previous beneficiary data. For each mother, we have information like age, income, education level, etc., and engagement sequence. She was not engaged, she got a service call, she got engaged, etc. So given this past beneficiary data, we can cluster these mothers based on their transition probabilities that we have observed. And then we can learn a mapping from the features, age, income, etc., into these clusters, meaning we get a mapping when a new mother arrives from her features into her behavior, her transition probabilities of bad state to good state upon intervention or not, Given that, we can compute her vital indices and then choose the top K mothers to give a call to. Clustering here compensates for the lack of data. And also it speeds up the vital index computation because we are not computing vital index for individual mothers, but just the one whole cluster at a time. Okay, so having computed vital indices, selecting mothers, we ran this field study of 23,000 mothers. This is the first large-scale application of restless bandits for public health. We divided the mothers into 3 groups, 7,667 per group. One was a restless bandit group, one was a round-robin group, and the current standard of care group where no call was going out. This is the current standard of care. In the restless bandit group, we pulled to 25 arms per week for 7 weeks. We gave service calls to 225 mothers based on the vital indices that we had calculated. For the round robin, we selected the first 225 to give a call to, then the next 225, then the next 225, etc. And our question is, how many more health messages have been listened to in each of these groups compared to the current standard of care group? What we find here on the x-axis are the number of weeks, on the y-axis, how many health messages more did the mothers listen to? What we find is that the restless bandit group at the end of 7 weeks, more than 600 more messages were listened to compared to the current standard of care, whereas in the round robin group, there's hardly any improvement. In fact, if you look at statistical significance with the restless bandit versus current standard of care, the difference is statistically significant. With round robin versus current standard of care, it is not. What this shows is that you have to be careful, strategic in choosing who to call using service calls in order to get benefit out of these service calls. Dr. Aparna Hegde says in reaction to this work, as we are transitioning the software to ARMMAN, that we are able to reach out to more and more women each week and get them back into the fold and save lives because of AI. And a mother who was interviewed, who got the service call and started listening to messages, says, I follow all the advice and take good care of my baby. All of this is documented in a wonderful YouTube video, AI for Social Good, in partnership with ARMMAN. Please check it out. I say this because the team that made this video is a very talented team. So this is our next step now, is to transition this software to ARMMAN and help our goal for 2023, 1 million beneficiaries to be helped using our algorithm. And in the future then, transition to another program called Kilkari, which is similar to ARMMAN, but on an India-wide scale, which works with millions and millions of mothers. This 5.28 crore translates to 52 million messages going out. And so we are hopeful that we can be of assistance to these programs, helping mothers and babies. So what are some next steps? First, given all the data that we have with this 23,000 beneficiary study, we can now construct a more realistic simulation. And we can use that to compare our ARMMAN vital-based algorithm, restless bandit, to a greedy algorithm and show that this vital-based algorithm actually outperforms this greedy algorithm. So other topics of future work include this, looking at this entire data to deployment pipeline end-to-end. So today, the way we do this after immersion, we do this learning. The goal of learning is to maximize learning accuracy, mapping features to transition probabilities, and then separately in a second stage, optimize to choose the top K beneficiaries to maximize decision quality. So first, maximize learning accuracy, and then maximize decision quality as 2 separate problems. Unfortunately, maximizing learning accuracy doesn't align well with maximizing decision quality. I'll illustrate this using a simple illustrative figure here. On the x-axis is a feature. On the y-axis is the transition probability of a restless bandit. So this is a notional example. The blue dots are all low-risk mothers. The red dots are all high-risk mothers. Our goal here is to figure out, to predict the transition probability and then select high-risk mothers. Now, to the left are all the blue dots of this orange line, and to the right are all the red dots. If we are asked to choose, given a linear regressor, choose something that has a high learning accuracy, you would learn that green line, which has high learning accuracy, but it doesn't predict the high-risk mothers. It has low decision quality. A decision-focused approach modifies the loss function to directly maximize decision quality. What this means is it will learn as a linear regressor, the green line shown. It is low in terms of learning accuracy. We can clearly see it does a poor job of predicting the blue dots, but it's good at predicting the red dots, which is what we want, allows us to achieve higher decision quality. We've applied this decision-focused learning in the context of ARMMAN in simulations and shown that if you go with a two-stage model, it indeed achieves higher predictive accuracy, but lower overall quality. And decision-focused learning, exactly the opposite, lower predictive accuracy, but higher policy performance. Another area of application is tuberculosis. Tuberculosis is a devastating disease around the world. In India alone, it causes 500,000 deaths per year, and 3 million people are infected every year. A TB treatment requires patients to take pills for 6 months, day after day. I get tired if I'm told to take these pills, some course for 7 days. 6 months is a very long time, and people drop out of the program. But it's bad for them because they don't recover, leads to drug-resistant bacteria. And therefore, health workers are again tasked with calling these patients to remind them to take their pills. So again, you have a health worker, they have a number of TB patients here under their care. You can choose, the health worker chooses to call the first 3 patients here. She then comes to know that 2 of them shown in green had taken their medicine and the red one had not. She has to choose who to call tomorrow as the next 3 patients to call. She may call these 3. The point here is that you may see similarity of this problem to the problem I've shown with ARMMAN, except that we have partial observability. We do not know if a particular patient has taken their medicine or not. To address this problem of restless bandits with partial observability, we came up with this model called collapsing bandits. Essentially, when there's no observation, we update our belief in the adherence that the patient may have. So we have some probability that the patient was taking their medicine. We update that probability. When there is an observation, though, when we give a call to that patient, the patient may say, hey, I took my medicine last night. Uncertainty collapses. We go to green state. Or the patient may say, I didn't take my medicine. Uncertainty collapses. Now we know their exact state, red state. This collapsing nature where uncertainty vanishes, we get direct information, is what we exploit in building up a faster algorithm. And we can show optimality guarantees based on this property of collapsing uncertainty. We have shown in our NeurIPS paper that this newer algorithm based on collapsing nature of this bandit leads to much faster runtime compared to the best baseline, while losing very little in terms of solution quality. There's many other interesting challenges in terms of index Q learning, in terms of risk-aware restless bandits, and so forth. So important area of work, not much has been done in many of these areas in terms of robustness and so forth. So I invite people who may be interested to get active in this area. Let me now switch to a second project, which is HIV prevention, and this is using social networks. So this problem was motivated. I was at the University of Southern California at the time. Right outside our campus were encampments of homeless youth. And so there's motivation to try and see what can we do for them. Here, there's 6,000 youth who sleep on the streets of Los Angeles every night. The rates of HIV in this population are 10 times the rates of a normal house population. Homeless shelters cannot reach out to every one of these youth, so they use a method where they'll invite peer leaders, educate the peer leaders about HIV prevention, expect these peer leaders to talk to their friends and their friends to talk to their friends, and information to spread in the social network. This is face-to-face interaction. This is not happening over Facebook, etc. So what we need to do here is influence maximization. We want to choose key influencers, key peer leaders, such that we maximize the expected number of influence nodes, those who come to get informed about HIV prevention. Here's a picture of one of our social work colleagues educating these peer leaders about HIV prevention. Now, information is supposed to spread via this independent cascade model. So you educate a youth C about HIV prevention. There's a fixed probability 0.4 that their friend D would get informed about HIV prevention. And if D is informed, there's a probability 0.4 that E will be informed about HIV prevention. So here, there's been 20 years of work before we started applying social network algorithms for HIV prevention. But in applying these algorithms to our problem, we noticed there are some real research challenges. And why do they arise? Because this fourth lesson I wanted to highlight, lack of data and uncertainty is a key feature of the AI for social impact work. First, I said the probability set is set to 0.4, but we may have uncertainty in propagation, this probability information. We may not know this probability exactly. Second, we call influencers, these are youth under difficult circumstances. One of them, when you call them, may get arrested on their way to the homeless shelter. One may choose to have run away and send their friend instead. So we need a multi-step dynamic policy to come up with backup plans when youth peer leaders don't show up. And finally, the social network, which is assumed to be known in many of the previous problem formulation itself is unknown. All we can have is a limited query budget to query a few of these youth and sample the network to uncover a part of that network. So how do we address these problems? I'm going to sketch some of the ways we solve these. So first, I said, previous work had generally assumed if you inform a youth C, we know the exact probability 0.4 that youth D will be informed about HIV prevention. In reality, we don't know exactly this probability. We may sample it from some distribution, but the mean of the distribution may itself be not known, and we may say it lies within some interval. So now we have this problem of robust influence maximization given this uncertainty. And we solve this problem by casting it as a zero-sum game against nature. So the algorithm is trying to choose peer leaders to maximize influence. Nature is trying to choose parameter settings to cause our algorithm to perform as worse as possible. We are trying to maximize, and nature is trying to minimize, where the payoff is the outcome of our policy compared to the optimal possible had we known nature's parameter settings in advance. If you're interested in more details about the mixed strategies and pure strategies and so forth in this work, we have our paper at ARMMAN 2017. Let me just sketch for you how we solve this game to give you an intuition. So if you imagine a social network of 400 youth and you're trying to choose 40, that's 400 choose 40 different choices for the influencers, a massive number. And nature is trying to choose parameter settings from a continuous interval, which is a massive set of strategies for nature. So this game is so large, trying to solve it is difficult. I mean, even representing it in memory is difficult. Therefore, we use a double oracle approach. Essentially, we initialize a small number of strategies for the influencer and nature on both parts, for both agents. And then we have this iterative algorithm, an influencer oracle that will provide its best response. Nature's oracle provides its best response. So the game grows. And we keep iterating in this fashion until convergence. And often we converge very quickly with approximation guarantee. So we can solve this game without actually expanding all of the strategies at all. So this is the way we get to a robust strategy. Let me sketch out this issue of not knowing the whole network in advance. You can imagine that we send our social network colleagues to homeless shelters and ask them to figure out who's friends with whom. But this can be very costly because that means they would have to spend enormous amounts of time trying to figure out the whole social network. If instead we can give them a simple task, like let's query 15% of the nodes in the graph. So we ask 15% of the youth, who are your top 5 friends? And something simple like that can be done easily. And now we have uncovered a small fraction of the social network. And based on that, we choose K peer leader nodes to spread influence in such a way that the performance is similar to the optimal possible had we known the entire social network in advance. So the key here is how do you sample these 15% youth? And so we've come up with this sampling algorithm. In a sense, it's sampling nodes randomly. but it's estimating the sizes of the communities that the nodes belong to, and then chooses seeds from the largest K communities. We can provide some performance guarantees for this algorithm, but let me jump now to the experiment that we ran. So our algorithm is called change. It's got the network sampling, the robust policy generation, and then it selects peer leaders. We ran an experiment with 750 youth. So this is a study conducted with Professor Eric Rice in the School of Social Work at USC. There's 3 arms in this study: change, which is our algorithm, 250 youth in this arm; degree centrality, which is the traditional approach, bring in the most popular youth, 250 youth in this arm; control group, no intervention at all, 250 youth in these arms, in this arm. And now we want to know at the end of 1 month and at the end of 3 months, what was the actual change in behavior? So actual reduction in HIV risk behavior. And what we find here, this is as, again, first large-scale application of influence maximization for public health done in collaboration with 3 homeless youth shelters in Los Angeles, My Friend's Place, Los Angeles LGBT Center, and Safe Place for Youth. So having done this study, at the end of 1 month, if you look at reduction in condomless anal sex, which is one of the HIV risk behaviors, change has more than 30% reduction in this HIV risk behavior. Degree centrality and control, there is no reduction. At the end of 3 months, degree centrality begins to catch up with change, but change is still better. And the fact that change manages to cause this reduction faster is important, because this is a HIV risk behavior, and also because people come and go, and therefore having this reduction happen faster is important. We also looked at another HIV risk behavior, reduction in condomless vaginal sex, and again we can see that change is superior. There are statistical significance results in our papers, and here's what our collaborator had to say.
Beautiful way to kind of like marry this tech world with this social service world, like, and how we can kind of go deeper and impact young people and elevate them.
There's lots of areas of future work. One is ensuring fairness in influence spread. You can imagine that, in fact, in these networks, because there are different communities, people of different racial groups, for example, that the influence spread is not equitable. How to deal with this disparity is one area of future work. Another is use of reinforcement learning to maximize influence spread. And so that's been an active area of work. With this now, let me switch to the third project, which I wanted to cover quickly. This is related to modeling COVID-19. And so we've written a number of papers in this topic, starting, of course, when COVID spread worldwide. I want to highlight one paper which might be of interest here that appeared in Science Advances and gets referred to in the popular press several often. So this was work done with Professor Michael Mina in the Harvard Chan School of Public Health. So Michael came to us with a modeling challenge that talked about what test to use. So if you're Harvard and you want to test all of the students and isolate positive students, should we be using the PCR test, which is the gold standard, which detects low viral concentration, but is costly, and it may take up to a day to get results back? Or should we use this rapid test, this antigen strip, which requires higher viral concentration, but is cheap, but we can get results back very quickly? So which test would you use? Now, we built up an agent-based simulation for this purpose. And on the y-axis here are total number of infections. The first simulation we ran were more testing all of the students on campus, isolating students if they're positive. We assumed here that results come back instantaneously. So indeed, if we can run a rapid test or PCR at the same frequency every 3 days, and we can get results back instantaneously, then the PCR test is better. It leads to lower number of infections. However, if we have a 1-day delay in getting results back, because as we said, getting the results back from PCR test takes longer time, 1-day delay in isolating as a result individuals who are positive, that negates all of the advantages of this PCR test. It leads to much higher number of infections. If due to cost, we can only run the PCR test every 5 days instead of every 3 days with the rapid test, again, the advantage of this PCR test of detecting low viral concentration is lost because there's many more infection. In fact, the conclusion is that rapid turnaround time and frequency is more critical than sensitivity for COVID-19 surveillance. So rapid tests is what we should go for. This work received a lot of attention in New York Times and Washington Post and Time and so on and so forth. We were honored when Dr. Anthony Fauci commented on our paper. And given Michael Mina's leadership, and we want to really say here that this is Michael Mina has been spearheading this use of rapid tests and has been an amazing leader in public health. Now with Biden plan, rapid tests are made available freely to American families. So in the last maybe 10 minutes or so of my presentation, I'm going to talk to you about a different topic, conservation and poaching prevention. So these are problems that arise in national parks around the globe. There's wonderful wildlife there, but there's threats to the wildlife due to poachers who set traps or snares to maim and kill this wildlife. These wire snares are placed by the thousands in these national parks. You can imagine a national park like the Queen Elizabeth National Park, which has got thousands of square kilometers of area, but say only hundreds of rangers to try to look for these wire snares. And you can see this is very difficult for a ranger to walk around and try to find these snares. So how can we help them? To that end, we divide the park into 1 kilometer by 1 kilometer grid square. And now we're going to ask them which of these, we are going to give them which of these areas are high risk, where they should search for these snares. We have 14 years of past data from Uganda, for example, which for each grid square tells us ranger patrol frequency. We have animal density, distance to rivers, roads, and villages. And the output here is to predict the probability of finding a snare per 1 kilometer grid square. I'm going to skip over the model just in the interest of time. The first pilot we ran was in fall of 2016. We were challenged to find areas where the rangers had not patrolled, but we predict that they will find snares. And so we chose these, we predicted these green dots. You see these green dots do not overlap with the red dots where previously snares were found. So these are completely new areas, 9 square kilometers each. We asked the rangers, go patrol these areas, you're going to find snares, even though you haven't patrolled these before. This happened to be 1 month before this ARMMAN conference deadline. So if we were to find snares, we would be able to publish a paper. If no snares, no paper. And so the rangers went out for a month. Every day we would get an email as to what happened. First, nothing. Then they said they had found a poached elephant with its tusks cut off. We were too late to save that elephant, but at least the machine learning model was asking us to go in the right direction. Then came good news. A whole elephant snare roll was found and removed. So poachers were active in the area. They were killing elephants, but before they could kill the next set of elephants, we were able to remove this elephant snare roll and potentially save lives of elephants. And then 10 antelope snares were found and removed. So this was a promising pilot test result. Following that, we ran a much larger test in 3 national parks, Queen Elizabeth and Murchison Falls in Uganda, Srepok Wildlife Sanctuary in Cambodia. In each park, we selected 24 areas. Some we predicted were high risk, more snares would be found. Some our model predicted was low risk, less snares would be found. These predictions were sent to the rangers. Of course, they didn't know which were high risk, which were low risk. They were asked to patrol them for 6 months and report back result. And these were all infrequently patrolled areas. And here's what we found. Where we predicted high risk, more snares were found. Where we predicted low risk, less snares were found. So this is really very promising in terms of assisting these rangers on their frontline work. In fact, now the PAWS system that we've developed is transitioning out, and I'll discuss more, to rangers. In Cambodia, in the Srepok Wildlife Sanctuary, the number of snare captures has jumped 5-fold from 2018 to PAWS being deployed in 2019. You can see more than 500 snare captures per month. And these are pictures from actual PAWS predicting and the rangers removing those snares. In March 2021, 1,000 snares removed. And so these are really very promising results. The end point now is that SMART, which is a collaboration of World Wildlife Fund, Wildlife Conservation Society, and 13 other wildlife conservation organizations, has integrated our PAWS prediction software into their platform. SMART is what is getting used worldwide by rangers. What this means is our PAWS software is now available worldwide to protect wildlife to thousands of national parks around the globe, for rangers to download the software and start using it to use these predictions. And we're seeing wonderful collaboration. So currently we have been working with Belize, in Zambia, and in Vietnam. And this is really a very exciting time in showing how we could potentially be useful as AI researchers in the important work that the rangers do in protecting wildlife across the globe. But there's very interesting future work challenges. So far, I've just talked to you about predicting where snares are. So if you imagine here, we've made these predictions, but now we have to also prescribe to the rangers where to patrol. So imagine in this 1 kilometer by 1 kilometer grid square, there's two areas we predict. One is very high risk, shown in red. One is low risk, but still important, which is shown in orange. And we said to the ranger, go to the highest risk point, which is shown in red, every day. A poacher conducting surveillance will know that the ranger is going to the red spot, and the poacher will just shift to the orange spot. So this is not good. Instead, we want to provide a ranger with a randomized policy. This we do by casting the problem as a Stackelberg security game. So that means that as a result of solving this game, we make recommendations to the patroller that 60% of the time they should go to area 1 red, 40% of the time they could go to area orange, shown in which is a lower risk area. So a poacher conducting surveillance will only know that the ranger is there 60%, here 40%. What the ranger will do tomorrow remains unpredictable. So these kinds of games are called Stackelberg games. And the main difference compared to previous work in this area is that we are not dealing with a fully rational strategic adversary. Instead, we have this boundedly rational poacher model that we have learned from past poaching data. So now how to solve this game when you have this boundedly rational poacher model and the model itself is not exactly known. So we do that again by casting it as the zero-sum game against nature, where our algorithm is going to choose patrol strategies for the rangers. Nature is trying to choose behavior parameters for our poachers to cause our algorithm to perform as worse as possible. Again, it's the same kind of max-min game. This was solved using reinforcement learning. There's lots of other areas. We've collaborated with a nonprofit called Air Shepherd that flew drones in Kruger National Park in South Africa. They took infrared videos. You can see in this infrared video, to spot a poacher or an animal, given all the white spots, is very difficult. The drone is flying way above, and you see these white hots, which you're not sure if these are just ground heat or people or animals. And to assist that, we built a system called Spot that automatically detects animals versus poachers and have delivered it to the nonprofit. But there's something very interesting then that can be done. A ranger flying overhead not only can spot poachers or animals, but it also knows down whether a ranger is present to stop those poachers or not. A ranger might only be present with the probability of 0.3. A poacher may only know that there's a chance the ranger is present, but they do not know for sure if the ranger is present or not. So the drone knows the ranger is present or not, but the poacher does not. We can exploit this asymmetry information to come up with an optimal deceptive signaling scheme. So we signal to the poacher by turning on our lights late at night and flying towards the poacher, sometimes when the rangers are present, sometimes when not, with optimally balanced probabilities. There's many other challenges. There's some parks where there's very little data. In these parks, it's important to balance exploration and exploitation, collecting data and detecting illegal activity. So these are new bandit style algorithms that we've been developing. So I've come to the end point of my presentation. Let me summarize some of the lessons that we've learned. Achieving social impact and AI innovation go hand in hand when we talk about AI for social impact. Partnerships with nonprofits, governments, and local communities is crucial for AI for social impact. We shouldn't be doing helicopter science when we do AI for social impact with communities, going there, getting their data, publishing a paper, and running away. We really need to be embedded to really deliver results. And this is a promise we make to any nonprofit that we get involved with. AI for social impact is about the data, the whole data to deployment pipeline. It's not just providing methodological contributions or improving algorithms. It's important to step out of the lab and into the field for this purpose. It's important to embrace interdisciplinary research with social work colleagues, with conservation scientists and others. And lack of data is the norm. It's a feature of these domains. I've had students who will complain that there's no data, hence there's no problem here. In fact, challenges such as a social network is missing are the research challenge. This is how you can earn your PhD. And this dealing with this lack of data should be part of the project strategy. If I may, let me just highlight one more lesson for students. There's a number that I have drawn out here, but in the interest of time, let me just highlight one. Interdisciplinary AI for social impact work implies less papers often, but the impact that gets generated matters. It matters obviously to society, but very practically speaking, for students who are interested obviously in graduating and getting positions and so forth, it matters to the selection committees and so forth. So rest assured, if you work in this area, that this impact will be counted towards your careers. There's so much more that I can talk about, but let me stop here in the interest of time. And thank you for being really patient listeners to this presentation. And I'm very happy to take your question. That's my Twitter handle, just in case you wanted to follow our papers. I will post our most updated papers and so forth on my Twitter feed. Thank you. Thank you for inviting me.
Thank you. Thank you, Milind. So there is a question from a Q&A from Prabhu. Thanks for talking about your incredibly impactful work leveraging computer science. I was privileged to listen to your lecture on parallelity in IIT Madras more than 30 years ago. And regarding your first use case, maternity and child care, is there a way to follow up on the veracity of patient responses? I ask because in some societies where some people like to please authority figures, they might be saying yes, when in fact they have not taken the medicine.
Wow, I am so grateful for this question. First of all, to Prabhu, I mean, that you remember a lecture from 30 years ago is amazing. I mean, you're being very, very kind. Now, regarding the maternal and child care, when the service call goes out, we actually know whether the mother was listening to the messages or not, because we have a record from the phone company that this voice message was listened to or not listened to. So the service call is not trying to verify whether they're listening to, or we already know, the state is known. We are giving them a service call to see if they have some complaint like, hey, you're calling me at the wrong time, or using, you are giving me a call in Hindi, it should be switched to Marathi, or maybe there's some other complaint that we can address, and encourage them to continue to listen to messages. Where your question is very relevant, though, is in the case of tuberculosis. There, it's partially observable, and the health worker is calling to check if the patient took their medicine or not. And there, indeed, a patient may say yes, in fact, when they haven't taken their medicine. And so this is a known problem. And we have some work that says, okay, what if there's a 15% or 10% error in the messages that are getting received? Exactly, they maybe know when they say yes, and what can we do about it? But it's an interesting problem, and trying to figure out what to do about it. We have tried to develop algorithms to deal with it, but much more remains to be done. Thank you for your question.
Yeah. Thank you, Milind. Thanks for the great talk. I also have a question about the last part for the Stackelberg and security game. So I'm curious, what is the input of your machine learning model for predicting the risk? And second is, do you also need machine learning model to predict, for example, the adversarial strategy of where they are going to place the snare and how like they might change their strategy in response to your defense? Yeah.
Wonderful question.
Thank you.
Wonderful question. The model we are using, so the way we predict where snares will be placed is based on a, so an adversary-based model essentially. So it's saying in the input is with what frequency did you patrol a certain area? So we know that the poachers will respond to that frequency of patrols. So in fact, we are the first to show that there is a deterrence effect. So if you patrol an area in the past month a lot, the poachers will shift from this area to a neighboring area. And so the model that we've learned essentially takes in as input your patrol frequency. It also then has other features like the slope of the land, distance to rivers, roads, and villages. And it uses all of this data in order to make a prediction of whether there's a high probability of finding a snare in that location or not. And so in terms of your game model, then your actions are already, so you have your actions, which are how frequently to patrol an area. And the adversary's action is based on your probability of patrolling an area reaction. So essentially you have an adversary model that takes as input the probability with which you have patrolled an area. So you have a game, a stack of work model where you act first, you patrol some area with certain probability. And second step, the adversary responds, taking into account the probability with which you have patrolled an area. And so that's how the game model gets built. Now, normally in a fully rational adversary case, the adversary will choose a reaction based on what is in their highest expected utility. However, here the adversary's reaction will be whatever is dictated by the model. So they will be not giving a fully strategic response, but a probabilistic response. You can think about it like a quantum response model. So, you put pressure on one spot, the adversary is going to shift to a slightly different spot, but in a probabilistic sense. Does that help?
Yeah, definitely helps. So that seems to be that the machine learning model also learns about the preferences of this strategic attacker's behavior.
Correct.
Because I guess like the disadvantage of a classical stack overlap analysis is like you need to make some assumption about the adversarial so that you can say they're rational and you can compute the best response. But in this case, it might be very hard to really know what is their preferences.
I mean, so in this case, we are lucky because it's also very unfortunate. On the one hand, as scientists, we're lucky there's data, but on the other hand, it's very unfortunate. There's so much poaching. There's a lot of data. And so given that, you can make a prediction about how the adversary will respond if you improve your patrols in a certain area. And so you can therefore come up with a good strategy for patrolling by basically, the adversary's response to your patrolling strategy. So you don't have to make any assumptions such as rationality. You just learn them, if that makes sense.
Yeah, that definitely makes sense. Thanks a lot. There is another question from Lavanya Marla. He says, thanks for the talk. This is Lavana, assistant professor at UIUC. For my research in such settings, I realized the data is evolving rapidly. I'm curious if these problems involve validation of the model and data on an ongoing basis and how expert opinion is incorporated even without the data.
Great point. We just saw this situation in our maternal and childcare domain. We went into COVID and then came out of it now. And so we expect people's behavior to actually change in this time. And so if you use data from pre-COVID for COVID times or during COVID for post-COVID times, there's going to likely be some errors in how we basically, develop this model and may start making predictions. So we have to indeed continually update the model and data. in reality, of course, I mean, as I mentioned, one other way we could handle this is by doing online learning in our Restless Bandit model, for example. So that's something that we're investigating, but the way we are practically dealing with it now is to just learn the model repeatedly. And a word of, I mean, what is also interesting, it's not just the behavior of the mothers and so forth, but you have often this nonprofit that you're working with, and they may change, unfortunately, meanings of data fields. So I'll tell you a very interesting episode. We had built them, you know, our algorithm, we're making, using this Restless Bandit, everything is going fine. And then suddenly the nonprofit starts telling us, hey, your algorithm is doing something wrong because it is calling mothers who are continuously listening to messages, and the mothers are complaining, why are they being called? They're already listening to messages. And so we were thinking, what happened? Why are we making such mistakes? And it turned out that the nonprofit had actually changed the meaning of 0 and 1 in their data. So 0 earlier meant that mothers were not listening. Now it meant mother was listening. So our algorithm was completely confused. It was making exactly the wrong predictions. And we had to deal with that. So yeah, I mean, we have to continuously check these models and algorithms, because there's lots of things going on. Not only are the behaviors of people potentially changing, but also we have these other data layers and so forth. You have to keep monitoring for that. Yeah, so thank you for that question. And indeed, it's exactly something we have to keep checking.
Yeah, thank you. Yeah, so thanks everyone. And if more people have questions, you can still post it. But we're about to reach this 1 hour time. And thanks, Milind, for the terrific talk. And I feel I really learned a lot about like how all these algorithms that we're familiar with, reading from all these NeurIPS and AI papers, when they go really into the reality and meet the social good, a lot more challenges and a whole new layer of complexity is added into the workflow of the framework. Yeah, so thanks a lot for teaching us. And thanks everyone for attending this seminar. And thanks, Milind.
Thank you, everyone. Thank you. Bye.
Yeah, thank you. Bye-bye.